Welcome to the first user training video for Conjecture System Identification, a program that helps you take the data from your industrial systems and create simple models of best fit. In this video, we're going to cover the main steps in using conjecture, and we'll start with dynamic systems that have a single input and single output. Conjecture is able to handle systems with multiple inputs to a single output as well, and we'll cover that in a later video. To get Conjecture on your computer, go to systemident.com/licensing. You'll need to download a copy of Conjecture and activate it with a license before proceeding with the training. In our previous video, we reviewed the concepts behind system identification and process control, and showed why modeling your systems with Conjecture System Identification can be immensely useful in understanding, diagnosing, and controlling your systems more effectively. The current video stands on its own, but if you want to watch the previous video before proceeding with this one, do feel free. We're going to start by looking at the simplest system that Conjecture is able to model, a system with a single input and single output. Here's a water pump system that we built as an example of this. We have a cylinder that is leaking water into a reservoir, while water is simultaneously being pumped from the reservoir back into the cylinder. We're interested in keeping the water in the cylinder at a set level, which is measured using this capacitance level sensor on the side of the cylinder. And we do this by varying the duty cycle of the pump motor, which is the percentage of time each second in which the motor is on as opposed to off. Our input to the system, therefore, is the pump motor duty cycle, going from 0 to 100%, and our output is the water level in the cylinder, as given by a capacitance level in picofarads. We use a PID control algorithm to vary the pump motor duty cycle using feedback from the capacitance level sensor. You can find the data we collected from this system in the Conjecture folder that you downloaded from the System Ident website. Click on Training Data, then click on the Water Pump folder. You'll notice that there are two files in this Water Pump folder. The first is the waterlevel_1 CSV file, which holds the data. And the second one is a text file which has a description of the data set along with its sample size and data elements. Let's open that to have a look. Now, when we look at the data elements, we'll note that the output, the water level in the cylinder, is in the first column, column A of our CSV file, and the input, the pump motor duty cycle, is in the second column, column B. We also note the sampling interval, which tells us that measurements are taken every 1 second. Close this and open the CSV file. So from the data description, we know that the output is in column A and the input is in column B. Notice that we don't use any column headers. What we're going to do is give Conjecture a plain file with just the data. We need to follow this format for any CSV we load into Conjecture. Output data goes into the first column, and then inputs, you could have one or more inputs, they go into subsequent columns. So depending on where you get your data from, you may need to shift your columns around to get them into the right format for Conjecture. And also be sure to remove any column headers in your data file. If we were to plot this data, we could see the input and output over time. Here we've got the inputs down the bottom in red and outputs on the top in blue. In Conjecture, we're going to model this data so that we can represent how the input relates to the output and gain a better understanding of our system. So now we're ready to load this into Conjecture. We open up the program and then we get this main window. The main window is divided into 3 sections: the model setup, hypothesis equation, and results. We'll start with the model setup. Click Load CSV and locate your data file. Select it and click Open. Now we've called this function loadCSV, but it's worth noting that the program itself doesn't actually store a copy of the file. You're just telling it where to find the file on your workstation in order to do all its calculations. A good place to start building models is to use the default settings for all the process dynamics for your system. Conjecture reads these from the data and generates initial guesses for the fields below. Click Restore to see these settings, and notice that the fields underneath all populate. We've also got a couple of equations appearing in the hypothesis equations section. This is the model we're building. It's often known as a time series model because each new data point depends in some part on previous data values. Let's look at both equations. The x1 denotes the input measurement, while the y1 denotes something that we call a filter, which is stored in memory while the output in the second equation is calculated. The k and the k-1 refer to the time points at which the measurements are taken, with k going up to however many time points you've measured in your data. So in the equation, we see that y1, measured at time k, is influenced by the previous y1 at time k-1, plus some amount of the previous input, x1, k-1. How much influence is denoted by the a and b values, which Conjecture will calculate for us. The output of the model is then calculated using the filter y1 plus an output shift, small a, which we'll explain shortly. Now back over to the model setup. The input shift corresponds to how much delay or time lag there is between the change in the input and the corresponding change in the output. We can change the input shift in the field here, and remember that input shifts are counted in the time units your data is in. So in the case of our water level pump system, each 1 in your input shift field represents 1 second of delay. Now we don't know how much delay there is in our system, so let's just use the default value of 1 initially, and then use the model plot and results to gauge how close we are to the actual delay. The filter shift field allows you to add time lags to the filter y1 as well. There is already one time lag, y1 k-1, by default in the model, which gives us a first order model. If we want to make this a second order model, we can add filter shifts to accommodate more complexity. To do this, just add your shifts separated by commas within the same set of double brackets. And see how another y1 term with a k-2 shift gets added to the hypothesis equation. This gives us a second order model, which is more complex. Now, unless you know for sure that your system is a second order system, it's best to try the simpler model first. So that's what we'll do here. We're going to remove that second term and stick with the first order model. Now for the output shift, and there's a checkbox here. If we check or uncheck this box, this changes our second hypothesis equation. So we either get output equals yk plus small a if we check the box, or just y1k without the small a if we uncheck the box. This small a is the output shift. So why do we need an output shift? The reason for this is that the modeling for the first hypothesis equation assumes that when the input x is 0, the output will steady state to 0. Now in some cases this is true, but it isn't the case for most industrial systems. So we need to allow for a vertical shift to the output to represent its steady state with 0 input. Now this is difficult to do with traditional system identification programs, but with Conjecture, all we have to do is specify that we want an output shift included in our model, and then Conjecture will estimate the value of the shift for us. So with our water level pump model, we're going to leave the output shift box as checked, and then we're almost there. The last part of model setup is the initial conditions. This is the first guess for A, B, and small a that Conjecture will run through its machine learning algorithm and ultimately calculate better estimates. The order of the estimates is always all the big letters first, so A and B here, and then small a at the end if we checked the output shift box to include it. Now we can just leave these as is, there's rarely any need to change them. And we're almost ready to calculate now. We just need to ensure that the plot model button is on. This allows us to view a plot of our model and process, and then we hit calculate. Alright, so since we opted to plot our model, we have a plot window that's opened up. I'm just going to expand this to full screen. We have the input data that's graphed in red and our output data graphed in blue. We're going to refer to this as our process output or process data. And on top of that, we have the data that's been generated by using our model to predict the output. And so this is going to be our model output or model data, and that's in green here. What I'm going to do is zoom in on the process output and model output by clicking the zoom button and then clicking and dragging across the range of data that I want to see. So up close, we can see the fit of the model, which is the green, to the process in the blue more clearly. And for the most part, this is a pretty decent fit. There is some error. We can zoom in on that here. And we'll look more at the use of that soon, but generally the overall trend of the process is reflected well by the model. If you want to zoom out, you can either click the home button to go back to the original plot view, or you can use the back button to go back through your previous views. So if you did several zooms, like the two that we did here, you can go back through each one of them in reverse order. So like that, 1 and 2, which takes us back to our original plot view. And then you could use the forward button to go through your views again in the order that you made them. At any point, you can save the plot view you've got by clicking the Save button, and that will save it as a PNG file. So feel free to do that if you wish, and then we'll close the plot window and look at our results window. The results window has now populated, and we can see that Conjecture has estimated values for A and B in our hypothesis equations, as well as for little a, remember that's our output shift, and a couple of other values as well. So A is the influence that each output value has on the next, which is always going to be between 0 and 1. Here A is around 0.996, nearly 1. And B is the influence of the input value with its delay, which in this model is very small, that's less than 0.001. And Conjecture has estimated the output shift, or little a, to be around negative 0.86. And then we have an estimate of the gain. This is the value by which the steady-state output changes in response to a 1-unit input change. So this here is telling us that a change of 1% in the duty cycle of the pump motor corresponds to a steady-state change in the same direction of 0.19 in the water level capacitance in picofarads. And then there's the error squared. This is a measure of how different our fitted model is from our process. The error squared generally gets larger the more time points you take, so we tend to take our error squared and divide it by the number of samples or time points over which we took our data. This way we get the mean squared error, and the smaller the mean squared error, or MSE, the better the fit. Normally we'd have to fit a few models and compare their mean squared error, and then that gives us a sense of what our best fit model might be. For this model, our mean squared error is round about 0.1. It's always good to fit a few models to any data you've got just to get some comparisons. So what I'm going to do is to do a refit for this data. So let's go back to our model setup. We're going to refit our model with a different input shift value. If you want to add multiple input shift terms, just separate them by commas, but keep them within the double square brackets. So for example, if we wanted to add an input shift of 10, we just put comma and then 10, something like this. And you see how the hypothesis equations now have another x1 term added to them with the delay value of 10 that we've specified. And then Conjecture will also calculate a value for C in addition to A and B. You can pretty much add as many input shift values as you want, but it's usually best just to do the one shift value at a time, as it's easier to compare your models that way. So in this case, let's try a larger input shift this time. So let's take the 1 away and go with a single input shift of 10. We can leave the filter shift the same, like we did for the first model, and also keep the output shift box checked because we want to include it. Make sure we have plot model on, and then hit calculate. And you can see how easy it becomes to calculate a couple of different models to compare. So now we have a new plot for a new model, and let's zoom in again. Now we can see that this is a pretty good fit to the process output overall, and if we compare this to the first model plot that we saved, the fit is actually an improvement. When we look at the results section in the main window now, we see that A is again around 0.996, and that the B in this model is still very small. The output shift is now around -0.42, around half the size of the shift that we got for the first model, and the gain is still pretty close to the first model, around 0.18 as opposed to 0.19. If we go to the toolbar at the top of the main window and click File and then Result List, we get the stored results for all the models we've run so far in this session. Here we can see that we've got the calculated MSE, or mean squared error, for both models, which is a comparable measure of how well the models fit the process. We have the solutions, so for each model we've got A, B, and small a. And no matter how many terms your model has, they always go in alphabetical order, and then if you check the box to include an output shift, then 1 will be included. Small a will be last on that list. And then if you keep scrolling to the right, you'll find the process dynamics that you specified in each model setup, the input shift, filter shifts, and the initial conditions. Now you can sort your models in order of the mean squared error. This is particularly helpful if you have lots of models in your list. So if you scroll all the way back to the left and then at the bottom, click sort error. Now if you do this a few times, you'll see that it alternates between sorting in descending order and ascending order. And either way, you should be able to identify the model with the smallest MSE. So we can see that at 0.095, our model with the 10-second delay is a better fit to the process than our model with the 1-second delay. Just to illustrate another refitting with a not so good fit, I did a refit with an input shift of 20. If we look at the results list and compare the results of the 3 models, we can see that for all 3 models, A is round about 0.996. The estimates for B do differ from the second significant digit onwards, and for the output shift as well, the estimates do vary quite a bit. So these models are quite different and give us quite different results. And as to which is the best fitting model so far, when we sort the error, we find that it is the model with the 10-second input shift that fits best. If let's say we want to delete the results for the poorest fitting model, we can click on that row and then click Delete Row at the bottom of the window. or else we can clear the whole set of results by clicking Clear All. Just note that any deletions you make cannot be undone. Click Cancel to exit. If you want to get as precise an estimate of the delay as possible, you can continue to refit the model with different input shift values, narrowing down to find the model with the lowest MSE. From that point on, you have a model that you can use as a digital representation of the water pump process. If you do this with your industrial process, you can gain a better understanding of your process and use that in diagnosing plant issues, running simulations, and improving your control. So now we've covered all the key features of conjecture system identification and how to use it to model an industrial system with one input and one output. In our next user training video, we're going to look at modeling an industrial system with nonlinear properties. If you have questions or feedback on this video series, please contact us at Conjecture Data Solutions. Thank you for watching, and we hope you enjoy using conjecture system identification.